Hello and welcome to a new video. This is for Precalculus using the Math UC homeschool curriculum. We're on lesson 15, Radian Measure. So to start this off, we could think about a couple questions here. One, why are there 360 degrees in a circle? And two, what if there was a better way to represent angles? What would that look like? So the first question is that we don't actually know for sure because of how long ago 360 degrees started being used. And so, the farther back you go, the harder it is to know things accurately from a historical perspective. But one of the most popular theories about why we have 360 degrees in the circle has to do with the same people that we attribute our 60 seconds to a minute and 60 minutes to an hour. That was the Babylonians, I believe, and that they really liked the number 60 because of how many numbers divide into 60 evenly. It's a pretty nice number in that respect. And so they liked the number 60. They actually, supposedly, I don't know how accurate this is. I'm not going to cite my sources. You can look it up if you want to. But one idea is that they also really liked 360 because they made their calendar year 360 days. And then for the extra 5 days that we, of course, have in a year, they basically had like a 5-day festival and celebration, which, by the way, I think sounds awesome. I think we should kind of go back to doing that. Although I guess we do kind of do something similar between Christmas and New Year's and all the other holidays. So anyway, that is likely why 360 is the number of degrees in a circle. So there's a light mathematical reason, right, of that, okay, lots of numbers divide into 360. That is nice. Because also keep in mind that as long ago as this was, we're talking like 4000 BC, maybe 2000 BC, somewhere in between there. I realize that's a big range of values, but we're talking about a long time ago. Possibly or probably at that point, they didn't use decimals to represent numbers. So if they were going to represent a number that was part of a whole, they were using fractions. And so having the ability to divide up into really accurate fractions may have been something that they found helpful. So that is a mathematical reason for 360, but in today's society, where we're not as into 60 and 360 as people once were, you might ask yourself, well, what if there's a better way to do it, right? So kind of thinking about degrees as a unit that we use 360 degrees, are there other units for angles? The answer is yes, there are. There's actually a couple that I don't know that I've ever used and probably couldn't come up with their name, but somebody did at some point basically try to make a kind of metric system degree measure. So they divided a circle up into 100, I don't even remember what they're called, but like 100 kind of degrees so they could use base 10. But that didn't seem to catch on. So I don't know what that's all about. But today we're talking about radian measure, which is a unit of measure that that has caught on, at least for higher level math, because there are formulas and things that you might do in higher level math that actually work out easier if you use a different kind of measurement than 360 degrees for a circle. So we're going to explore that right here, right now. It's going to be awesome. Okay. The new type of measure we're talking about, radians, has to do with, it's weird because it's not like pick a number, divide the circle up into that number, which is basically what you would think of with 360, right? The base 100 one, it may be that each quadrant is 100 instead of 90, and so in total it's 400. That might be a thing, but that's not what we're talking about here. So you might think that, hey, that's the way to go. Pick a number that seems nice, divide your circle up into it. But radians takes a different approach. It says, what do we know about circles? We know that their circumference is 2 times pi times the radius. But the fact that there's a connection between the circumference of a circle and its radius means that we can actually think of angles in terms of radiuses. And so the word radian is very similar to radius, and I think that's probably like related somehow. So what we do is we essentially say, well, here's a radius that we have right here. This is the radius of this circle. Well, what would happen if I put that radius on the circle instead? What would that look like? So let's say that this is a radius of 1. What would it look like to have a radius of 1 on the circle? Maybe it would stretch to about here. This is going to be approximate. So we might ask ourselves, how many of those would fit around our circle? Well, it should be that we would have a little over 6 fit. And I really should have made it to where I could do this more accurately to show you. But basically, if I could stretch this line out accurately this way, then you should end up with about 3 and a little bit more here, and then 4, 5, 6, and then a little more. Because what happens is that we can fit in any circle, we should be able to fit about 6.28 radiuses in a circle. And that 6.28 is significant because that is what 2 pi equals. So what we do is we've got this radian measure that we get by saying, here, this is still 0 radians, but a full circle is now going to be 2 pi radians instead of 360 degrees. And then from there, we divide up the circle into pieces of 2 pi. Now you might be thinking, well, wouldn't it make more sense if we were dividing up pieces of 1 pi instead of 2 pi? But there's this connection to circumference, which is 2 pi radius. So let's think through this. If a whole circle is 2 pi, then half of the circle, which we're used to as being over here 180 degrees, half of a circle would have to be half of 2 pi, which would be regular pi. And if you've looked at a unit circle online, especially where they may have degrees and radians just listed on there already, then you'll have actually seen some of these values or all of these values that I'm pointing out to you. So it's, by the way, it is tricky to get used to radians at first, but it's something that as it goes on, you may end up, like, the more used to it you are, I think the more you'll like it, or the closer you'll get to liking it. I don't know. Degrees still feel like, even though I know a lot about radians, degrees still feel like they're more helpful to think about if I was to measure something to, like, build something, or like I don't know that I've ever seen, someone brought this up in class today, I don't think I've ever seen a protractor in radians, so it's not like, if we're trying to measure something to see what the angle is in real life, we probably would not use radians. Maybe mathematicians and engineers do, I don't know. But anyway, so halfway around the circle is pi, so if I think about 90 degrees, well, that's half of the way to pi, right? That's halfway to this 1 pi over here. So 90 degrees would be like having half of a pi. So each quadrant is half a pi, so we could keep filling things in. We could go further and actually fill in all of our unit circle values and kind of get an equivalent thing happening here. So we're going to do a few things today with radians. We're going to convert between degrees and radians. We're going to do it the other way as well. We're going to put some things into our calculator and look at some arc length problems. So let's check it out. Here's the things. Here's some important things to remember. First, we are going to use a conversion fraction for these when we go between them. And so the way we do that with like inches and feet, right, is that you would have 12 inches in 1 foot and you put which one is on top based on like what you want to end up with or what you want to cancel out. So if I could explain that real quick, this is just to kind of give us the idea of what we already should know how to do. And now we're adding to it a new type of converting, right? So if we have 10 inches and we want to change that to feet, and if you're in chemistry or physics, then you may think of this as dimensional analysis. I just think of it as math. But we know there's 12 inches in a foot, so we put the 12 inches on bottom because we want the inches to cancel. So we need one on top and one on bottom. And then because the feet are still there and they're on top, that means the units to this would be feet. So we get 10 over 12 feet, and then we simplify or whatever. So we're going to use 180 degrees equals pi radians. And that means that we put 180 degrees on top or bottom and pi on top or bottom, depending on what we want at the end, radians or degrees. Secondly, you do not have to label radian measure because for whatever reason, we just, as a mathematic community, have decided if it doesn't have a label, it must be in radians. I think it probably speaks to how much radians is actually used in higher level math, I would assume. But basically, it's like it actually makes more sense, I guess is what they're saying, to not have a unit. The Math You See workbook, I think, or curriculum, I think uses R next to it to denote radians, and that's fine, but you don't need to put an R next to it. Our answers are also going to often have pi in it whenever it's radians. So you could think of pi like it's our unit, but that's not really what's happening. It is a way to be like, oh, I think this is in radians because it has a pi in it. But it's not like, it's not quite the same as just saying like inches or feet or things like that. We're basically writing it with pi in it so that we don't actually have to multiply it by pi and get a decimal. And then third, if you're using radians on your calculator, specifically if you're doing sine, cosine, tangent, etc. on your calculator, this is where we need to switch modes. So on your calculator, if it's one of the newer TI-84s, you have a line at the top that shows you what mode you're in. So instead of being in degree, we would want to switch to radian using the mode button. I'll be doing my math on Desmos, and so there's a little gear button on the side. Desmos actually defaults to radian. So if you've been using Desmos, you will have been changing it to degree mode hopefully each time. But we want to just be in radian mode now. And at this point from now on, you will need to think about, as you do sine, cosine, or tangent, and say, wait, is this something that I need in degrees or radians? What did they give me? And that's how you decide what mode you want to be in. Okay, let's get started. Example 1, find the radian measure of each angle. Have a helpful parentheses here that says use 1 degree equals pi over 180 radians. Then find the decimal equivalent of each answer. I went ahead and put that helpful hint because it's in the workbook pages on this. But essentially, if we just know that pi equals 180 degrees, then we can just think, what do I want to cancel out? And that's what goes on bottom. So since it starts with degrees here, we want to cancel out degrees. So we're going to make the first number a fraction, and then have pi over 180, because that's going to cancel these degrees. It also introduces a pi in, which I said most of our radian answers will have pi in them. So in order to figure this out, we're essentially doing 60 pi over 180, but we're going to simplify that. We're going to ignore the pi, simplify the 60 over 180, and then write our answer with pi. So you can use your calculator to do that, or you can try to work it out in your head. There's this cool thing where these zeros would cancel out. If you have a 0 on top and a 0 on bottom, the zeros cancel. So then we have 6 over 18. Then we can keep simplifying so that this should end up being pi over 3. And then we would grab our calculator right here, and we would, it's basically just saying, hey, what is this as a decimal? And it may even in our workbook tell us to use 3.14 for pi. I'm not about that. There's a pi button on our calculator. I would rather, if it really wants us to find the answer, I'd rather we just use the pi button. It's over on the TI calculator. It's over on the right side. You have to press second and then the exponent button. But pi over 3 is approximately 1.047. So that would be our two answers. In the workbook, these are two separate sections. It asks you to convert, and then it asks you to convert the other way, and then it comes back and says, okay, write the first 4 as decimal approximations. So I just decided to combine it into one because I think that makes more sense personally. But each of these there's not really anything different or tricky about any of these. So at some point, definitely, you should try it on your own to see if you have the hang of it. Each one of these, we're going from degrees to radians on example 1. So that means that we want to do pi on top and 180 on bottom. So that the degrees cancel. It's amazing how hard it is to cancel out that circle or hit that circle. Since it's a negative 30, our answer is going to end up being negative. Because just if we have a negative times a positive, it's a negative. It should hopefully make sense that if our angle was negative, that we could also write radians as negative angles as well. They just, like with degrees, it just goes the other direction. So we need to simplify 30 over 180. Now 30 goes into 180 6 times. So that means that this simplifies to be pi over 6. So negative pi over 6 is our exact answer because we haven't rounded. And then pi over 6 as a decimal, I can go back over here and just change that, 0.524. Okay. 110 degrees. Let's see. Put that over 1, times it by pi over 180. And so the degrees cancel out, and we could cancel out a 0. That would give us 11 over 18, which doesn't simplify. So our answer here is 11 pi over 18. And then we figure out what that is as a decimal. I'm going to be honest, there's not really much of a reason to change these to decimals other than it helps you see what the actual values of these are. Leaving the pi in makes it seem kind of abstract. So I get that. This would be, oh, I missed the 1. 1.92 is the answer to this one. 1.920 because it rounded up. So I don't see much point now that we don't use trig tables anymore in finding the decimal approximation. I believe that is one of the reasons why you might decide to do that, because a table of values, instead of having them in terms of pi, I would assume that they have them in terms of decimals. I don't know for sure, but that's the assumption I'm making, because I still have not ever used a trig table. Let's cancel out the degrees, and we cancel out the zeros. So we've got 27 pi over 18. That's not done yet though, because these both have a 9 I can simplify. You also could just simplify these on the calculator, but I would recommend that you do that without putting in the pi, because putting in the pi, it's just going to give you the decimal approximation. But if you type in 270 divided by 180, and then do math enter, it will change it to a fraction for you, and it basically would have told us it was 3/2. So that's pretty nice. 4.712. All right, so now we're going to go the other direction. Now we have radians, and we're going to find degrees. And our helpful hint has flipped this upside down because we're now going the other way. So it should make sense that we want, instead of putting the degrees here, I would have, because I just basically copied this out of the Math UC workbook to make it look similar, I would have put 180 degrees here, because that helps us see, okay, we're introducing degrees on top. That's what we want. We're also canceling out pi, which is nice, because just in general, we don't usually see degrees in terms of pi. It's not something that makes a lot of sense to do. So we're going to times each of these by 180 degrees over pi. Similar things should happen. The pi's cancel. I guess not similar things. The opposite should happen. Your pi's cancel this time instead of you introducing a pi. We could do 3 times 180 and then divide it by 4. We could do 3/4 times 180. There's actually lots of options here. And so you might play around with it some if you aren't sure how you want to set this up. But literally you could do 3 times 180 divided by 4. And even though it grouped it weirdly, that is still correct, because multiplication and division is kind of weird. Like even if I put the 3 on top, it still is saying the same thing. I don't think I can do that. Well, yes, I can. See, still the same thing. So this is 135 degrees. Voila. 19 pi over 18. So we're going to times this by 180 over pi. So the pi's cancel. This is a case where if you wanted to do it by hand, it might not be so bad, because if you look for things that cancel with 18 and 180, in this case, 18 cancels and leaves us with 10. So then we do 19 times 10 and get 190 degrees. But you can just type it in your calculator, and that's fine too. Let's see, 180 over pi. So these pi's cancel, and so I could cancel a 3 out and be left with 60. Then 4 times 60 is 240, and it is negative because of the negative at the beginning. So that's me being lazy and not using the calculator, which, you know, you might be lazy and want to use the calculator, and that's fine. Like, because we can just do 4 times 180 and then divide that by 3 and see we get 240. Or I could have put the negative in as well, and that would have given me negative 240. Let's see, 4 pi. 4 pi or not 4 pi? Well, that doesn't quite work. So we're going to do 180 over pi. So the pi's cancel. There's nothing to cancel out with the 180, so we do 4 times 180. We also probably could have come up with this just by thinking about, well, if one circle is 2 pi, which is 360, 4 pi would mean I have 2 circles. So I need 2 360s, which means I need 720. So that'd be my answer. Let's look at the next one. Example 3. So we're just going to do A here, I think, and this is where we're going to use our calculator. This is where, if you haven't already, you need to switch to radian mode. What we did before now with putting pi in, that is the same whether you're in degree or radian mode. But as soon as we start using a trig function on our calculator, that's where we need to account for what mode we're in. So we are going to find sine, cosine, tangent, cosecant, secant, and cotangent of pi over 6. Now, there's an issue here, and part of it I have is an issue with MathUC and the terminology they use, although I actually finally figured out why they're calling it what they are. So sine, cosine, and tangent have inverses. Those inverses are not cosecant, secant, and cotangent in the way that I think inverses are actually used, the terminology. So an inverse of something is where you switch the x and the y. So if we had something like y equals x squared, the inverse of y equals x squared, which hopefully you did this in algebra 2, but I don't know if you did. The inverse of y equals x squared is where you take the x and the y and you switch them, and then you typically will solve that for y. Inverses have relationships with each other that are kind of neat. So like, if you know one is a function, the other one doesn't have to be a function, and there's all this stuff that goes with inverses. We do use a -1 exponent for that. You might use, f of -1 to represent inverse. So this is kind of a tricky thing, okay? But when we talk about inverse sine, and when we use the second sine button on our calculator, this is the kind of inverse we're talking about. I prefer for cosecant, secant, and cotangent to use the word reciprocal. Cosecant, secant, and cotangent are reciprocals of sine, cosine, and tangent respectively. So to get 1 over cosecant, you do 1 divided by sine of your angle. To do secant, you do 1 divided by cosine. To do cotangent, you do 1 divided by tangent. Now here's where calculators matter, like what kind of calculator you have. Because one of the best things about the TI Inspire that makes it actually maybe preferable to the TI 84 at the level of math you're at is the TI Inspire has cosecant, secant, and cotangent buttons. Okay, so that's nice. Desmos has an actual cosecant, secant, and cotangent button. The TI 84 family of calculators, anything with an 80 something, they do not have a cosecant, secant, cotangent button unless it's hidden somewhere. So what you have to do to find cosecant, secant, or cotangent is either do 1 divided by, that's always how I've done it, or there is this button on the side of your calculator that says x to the -1. It's over on the left side about halfway down. This will also give you the reciprocal. So you could do sine of the angle and then press that button, and it should give you cosecant of that angle. It's a weird thing. It's something that I hadn't even really realized was going to be an issue until class today, so that's my attempt at kind of clarifying that. We have not found cosecant, secant, and cotangent on the calculator, I don't think. We found inverse sine, inverse cosine, and inverse tangent, which was us finding the angles that went with certain sides, and those are 2 different things. So let's give this a try. First off, it wants us to write this as a decimal. That's actually not super needed these days because we don't have to use trig tables anymore. But if we're filling out the table, right? So pi over 6 is 0.524. So that's what I'm going to put here. sine, and I'll go ahead and drag this over actually, because I want to show you, if you are using Desmos, you show the keypad. You can do this on your on the phone app as well. You want to go to functions and see right here we have sine, well, I guess we'll do sine, cosine, and tangent, but see how it also has cosecant, secant, and cotangent. So easy peasy. I actually want to do sine of pi over 6. So we could use the decimal we got a second ago. That would mean that we're rounding, and I'm not really a fan of that. So I'm just going to go ahead and do sine of pi over 6, which is 0.5, also known as a half, which makes sense if you realize that pi over 6 is the same as 30 degrees, and sine of 30 degrees is 1/2. So just throwing that out there. Cosine is cosine of pi over 6. What's really neat, and you can do this actually kind of on the TI as well, is that for the TI-84, you could scroll up and highlight sine of pi over 6 and press enter, and then just go over and change the sine to a cosine. And it's a few, I think, less keystrokes maybe than having to keep typing pi over 6 over and over again, but 0.866 is what I would use here. Tangent. So tangent of pi over 6 is 0.577. So now we're going to do 1 divided by sine of pi over 6, 1 divided by cosine of pi over 6, 1 divided by tangent of pi over 6. Or we could use the actual secant, cosecant, and cotangent buttons. I can show you that those give us the same thing. So 1 divided by sine of pi over 6 is 2. That actually makes sense because if sine was 1/2 and we're reciprocaling it, it becomes 2. But let me show you with the function button that you can't see here. Oh, I meant to do it on the next line. Actually, I don't even have to use the button. I can spell it out. Well, 2, see? It works to be the same thing. That was just to hopefully help you believe me. So 1 over cosine pi over 6 is 1.155. And 1 over tangent pi over 6 is 1.732. There you go. And I'm just not going to do B right now because I don't want to. Let's do arc length. So this is one of the cases where if we were to compare this formula where we have radians to start, and with the formula if we had degrees to start, you would notice that radians makes it easier. And that's essentially because we are trying to find part of a circle. And so if we do that with degrees, we basically end up having to do the angle we're given divided by 360 and use that fraction to figure out like the percentage of the circumference we're talking about. It's not impossible by any means, but if we were originally given radians, that would be the ideal situation here, because if we are, then all we have to do is whatever the radius is times the angle of this arc, and that gives us the arc length. So let's say this was 5. We would, and that this was 3 pi over 2. Okay, we'd just say x equals 5 times 3 pi over 2. So that means it's 15 pi over 2. And we could leave our answer like that with whatever units 5 had, like maybe that's 5 inches. So 15 pi over 2 inches. We would change it to a decimal if that is the preferred way of writing it. But that's what we would do. Now, our problems on this are actually going to start with it in degrees. So even though the arc length formula is easier if you have radians, we're gonna have to convert to radians to use it. So that's kind of annoying, in my opinion. But we're very much stuck in using degrees a lot of times in the real world. Still, even though it does have advantages in higher level math and perhaps science or whatever. So just keep that in mind. I used 2 made up cities here because I did not want to have to look up 2 cities that have the same longitude this way. So imagine that this circle is like a cutout of half of the Earth. And so we're saying there's a city up here and there's a city down here. And so like how far apart are they along the Earth? What's the distance between them? If they had different longitudes, like they weren't directly north and south from each other, that would make our distance longer. We'd have to add more into that calculation. So this is kind of simplified in that respect. So we're going to find the distance between Rivendell and Mordor. We're going to assume, because I did not think to make this up earlier, we're going to assume that it's the same size-ish Earth that ours is. So our radius is 4,000 miles. And we're going to use 3.1. Actually, I'm just going to use the pi button personally. Remember to express theta in radians. So here's the deal. Rivendell is 44 degrees north. So Rivendell is up here. Oh, that was like a really bad R that I just tried to draw. This angle is 45 degrees north of the equator, in case that's not obvious. Mordor is down here, 16 degrees south of the equator. And it says the radius is 4,000. So we're going to use that formula, x equals r theta. But very first thing we got to do is figure out the angle and switch it to radians. So if it's 44 this way and 16 that way, we need to add those angles together to get this large angle here. So 44 plus 16 is 60. But we want to change that to radians. So 60 degrees times pi over 180. I put the pi on top right because I want degrees to cancel. So 60 over 180 simplifies to be 1/3. So this would be pi over 3. So we know r is 4,000. And our angle we now know is pi over 3. So we're going to multiply those together. We'll go ahead and get a decimal for that because, you know, why not? And what we will have found, by the way, if we do this, is how far Frodo had to travel from Rivendell, Frodo and Sam, from Rivendell to Mordor, assuming they went in a straight line, which I guess actually isn't accurate because I don't think they did go in a straight line. I think they had some bobbing and weaving happen. So 4188.79. That was a really great way of saying that. 4189 point. Wait. 0.79. Sorry. And this was in miles. So that's how far they would have had to trek. That's actually a really, really long distance. So hopefully that's not really the distance from Rivendell to Mordor. I don't know though. So that's how we find arc length, is convert to radians and then times by the radius. Hey, thanks so much for watching. In case you were curious about that 4,000 number, I did look that up because 4,000 is what Math-UC uses. And so the radius of the Earth is approximately 3,958.8 miles, although it does depend on where you measure it. Because on one hand, the radius to the poles and the radius to the equator is actually a slightly different number. And the other thing that was pointed out in class today for me was that, you know, if you were to measure to like the top of Mount Everest, in theory, that would be a longer radius, right, than if you were to measure, some Death Valley or, you know, a valley somewhere that's like, or the Grand Canyon. So there is some variance there. So I don't actually have any clue where this is being measured, this 3,958.8. If you Google radius of the Earth, that's what it tells you. So that's all I know about it. Anyway, thanks for watching. I hope you liked the video. I hope you like the video. Not like, but like, I hope you press the thumbs up button on the video to let me know that you thought it was a good video. If you didn't think it was a good video, just don't even bother because I don't look at the dislikes. So thanks for watching. Have a great day and see you in the next video.